and in this chapter we talk about block cipher operations. And before we go to block ciphers, we want to describe three extensions of DES. And I don't know why the author decided to write these three extensions of DES in this chapter. It has nothing to do with this chapter. But the rest of the chapter is about the modes. So we'll talk about those modes. But before doing the modes, we are going to talk about extensions of DES. We should have probably talked about them before AES. But we are just following the book chapter by chapter. So I left it here. So there are three extensions of DES: double DES, triple DES, DES-X, and then we go into modes. And basically, when you want to encrypt long messages which are longer than one block, you really need to use the modes. So we will tell you why you need to use the modes and what they are. And the modes have nothing to do with DES. Those apply to every block-oriented encryption, which means both DES and AES. And they will apply to triple DES as well. The first thing would be that as soon as they found out in '97 that DES is not very secure, people started working on extension of DES. So first thought that comes is, why don't we do double DES? Right? We take first key, encrypt it second time. It turns out it doesn't increase the security, it does increase the work. And this is how it works, because meet in the middle attack. And meet in the middle attack was developed by Diffie and Hellman much before all this happened, and even '97, in 1977. By the way, Diffie and Hellman, that name you will hear many times in this course. There are few crypto scientists that have really changed the world, and Diffie and Hellman are one of those actually. And then Rivest is another one of those. Okay, so Diffie and Hellman did a lot of stuff, and we will see them, throughout this course. And one of the things they did was they showed that in any encryption, if you do a double of it, you don't really benefit. And this applies to any encryption actually. So here's the thing. Suppose if ciphertext is equal to EK2 of EK1 of P, double encryption with key K1 and K2, right? Then you can write down that X, which is the answer you get in the middle, is equal to encryption of P or decryption of C, right? And so what you can do is, if you know P and C, you can encrypt P with all 256 keys and make a table. And just basically they are trading off memory for computation. So rather than computing it every time, you just compute it first and store it in a table. The table is 256 long. Then you decrypt C with all 256 keys, 2 raised to 56 keys, and actually you do one by one, and if you find any match, then you have found the keys. There's some probability that you may not have found the exact combination K1 and K2, so you have to do one more PNC pair. If you get one more PNC pair, then you can be almost sure that this is the pair K1 and K2. So you can find both the keys in total 2 raised to 57 operations, because you did 256 operations here and 256 operation here, 2 raised to 56 operation here, so total 2 raised to 57 operations. So all you did was you increased your security by 1 bit, although the work is much longer. So it's not a good idea to double encrypt. Alright, so people said, why don't we do triple? And triple works, because with triple you can get up to double. So even if you do man in the middle attack, you won't get 3 times 56, but you will get 2 times 56, because 1 times 56 is stored in the table. So, and instead of EEE, it's better to do EBE, and I will tell you why in a minute. But basically, so this is how triple DES works, is that you do encryption with key K1, decryption with key K2, and then encryption with key K3, because decryption and encryption are identical in this case. Right? Decryption is not any weaker or any stronger than encryption. It's exactly the same. So if you do D in the middle, Then there is some extra property that comes in that we'll see in a minute. And so EDE is same as EEE. Agreed? Everybody agreed on that one? Because D and E are same. Alright. So EDE sequence is used because if you use EDE and you put all the keys equal to, then that becomes single DES. So the new machine can talk to the old machine. The new machine is triple DES, old machine is single DES. If you want to talk to the old machine, then you set all your keys equal and you can talk to the old machines. And PGP and S-MIME. Now PGP is pretty good privacy. That's a public domain encryption system. And S-MIME is secure mail system. Both of them use this 3-key version where there are 3 keys. Most other places, but this 3 keys provide only 112 bits of security. Because of man in the middle, you can just paper table 56 bits, and you will get only 112 bits of security. Even though you are doing 3 times 56 work, you get 2 times 56 security. So people said, why don't we just use 2 keys? So the 2 keys are used, and in this case they use the first key again with in the third round basically. So you do encryption with K1, decryption with K2, and then with K1. And this is what is standardized as NC and ISO standards. And this gives you almost the same security as 112 bits. There are some theoretical attacks, but no practical attacks. So when people say triple DES, most likely they mean this one, EDE with 2 keys. 2 important things to remember. First important thing is why EDE? Legacy machines. And why 2 keys? Because third key doesn't give you any extra security. It is equally difficult to find just these 2 keys to raise to that many operations, 112 operations, as with the 3 keys. So that's why. This is a whole topic, key transfer. But brief answer is that every key, for every session, for every transaction, a new key is generated. So you don't use the key again ever. Alright? Now, so there is so much transfer to be done. Every time I want to talk to you, I want to charge your credit card, I have to have a key. New key between you and me. So then there is a public key encryption which is used to do that, to transfer the keys, which we haven't talked about, which we will talk about in the next lecture. So wait until the next lecture when we'll talk about public key encryption, which is much more complicated, but at least it allows you to send the keys without sharing a secret. Right now we have talked about only shared secret encryption, where we both have the key somehow. Once we have the key, then we can do the encryption. But the question is, how does the key get from here to there? Right? So the answer will come after public key. So there is one more extension which is not in the book, but at least in one private standard it is there, and it is done by the guru Ron Rivest. I said there are a few names in cryptography that you will remember. Rivest is another one. So Ron Rivest is the one who is R in RSA, and therefore the owner of the RSA Incorporated, and therefore a billionaire, a multimillionaire, I don't know what it is. So he is really, he has not only done practically, theoretically as an academic, but also as a business person, I would say. And he is very smart, and he has done many things, and his name will come, just like Diffie and Hellman, his name will come throughout. I have very high respect from him. He's a living person. So Rivest came up with this in 1984, and this is an extension of DES, in which he says that all you do is exclusive OR the plain text with a key, then you encrypt, and then you exclusive OR with the second key. So he doesn't want to do DES 2 times. He does DES only 1 time. But he does exclusive OR 2 times. You take a key, any key, and exclusive OR with plain text, then you run DES, and then you exclusive OR with second key. That, he says, will give you 184 bit of security, although with all these attacks and everything else combined, you will reduce it to 188 to 119 bits, which is very close to triple DES. Yeah, so I don't know why people didn't select that. See, this is another interesting thing, is that 1984, maybe it was a little bit too late. Maybe this was already there by 1997 when they did triple DES. So this was there, but basically, so this is only implemented in his system, in RSA's system. So he is selling it, but it was not, and it is quite possible that maybe he patented it. I don't know what happened here. See, if you patent something, then it is not accepted by the world, because they want free stuff, right? So maybe that is why it was not implemented. I don't know the story behind it, but I just thought I will mention this thing, and obviously the reference is Wikipedia. All right, so much about making DES better, but whether it is DES or AES, DES implements only 64-bit, which is like 8 bytes, and AES does 16 bytes. What do you do if the message is longer than 16 bytes? Well, it's not trivial, by the way. This whole chapter and this whole lecture, rest of the lecture today, is about what you do if the message is longer than 16 bytes, or message is longer than the block. So first straightforward thing would be that, okay, well, message longer than the block, we will use the same key for each block. If you do same key for each block, then all you are doing is you are taking this plain text and making it to this ciphertext, and somebody could just write a table, and they would know for each plain text what is the ciphertext. And the idea, this is why it is called code book scheme, electronic code book mode, ECB mode. So ECB mode is the simple mode where you just encrypt every block independent of the other blocks by the same key. Right? So there is a big problem with this. The problem is, there are two problems. First of all, you are using the same key many, many times, and every time you use the same key, you are putting yourself into more trouble because you are providing more data to the attacker. So you never use the same key, as I said a minute ago. You don't use the same key second time. Okay? Second thing is that the same plain text always gets translated to the same ciphertext, which is also a problem. Because if they got the same ciphertext, they at least know that this is the same plain text. They don't know the key. But if they have one PC pair, when they get it again, they know the P right away. All right? So that's not it. Actually, here's the thing. So again, this picture, if you encrypt with DES using ECB, this is the result. So what happened was, everywhere there was a dark, when it was encrypted, whatever it became that, every single time. So when you do the same thing again and again, the frequency doesn't change. Remember that frequency analysis? So the frequency of black and white has not changed that much. So this is encrypted message, doesn't look like very much encrypted. If it was really encrypted, it should look like this. This is what they call whitening. It should be all white actually, it should not be any color at all. Therefore, scientists got together, basically NIST again, and defined 5 modes that can be used with any block cipher. By the way, this picture came from Wikipedia. I thought it was interesting. It's not in the book. Alright, so you understand now why we don't do ECB? So first thing we do is, we do block chaining. Basically, we take the first ciphertext, exclusive out of the plain text, and then encrypt. So even if these two plain texts were identical, the ciphertext would be different. So this is called Cipher Block Chaining. Why? Because we are taking the cipher block and we are chaining it like that. So with this, the first problem is gone, which means that if you take the same plain text n times, you will get different ciphertext n times. However, one of the problems is that if you change anything here, that might change everything. Right? Because one bit change here will change that bit, that will change that bit, that will change that bit. So there is a big diffusion of error. Second thing is, what do you do with the first one? See, here you have to do something. See, here you are adding previous cipher block. What do you do here? So what they do is they take a what they call initialization vector, a random number, and they use for the very first one. Now that random number has to be sent to the receiver, because the receiver has the key but does not have IV, right? So in fact, in many places where I have seen, for example, in IPsec and all that, IV is sent in the clear, because before they get IV, they can't even decrypt anything. So anyway, but the thing about IV is that it has to be known to the receiver. If sent in clear, the attacker can change the bits of the first block and change IV to compensate. So that is an attack right here. If you change one bit here, then you can change the message, get the same ciphertext, or change the message and change the IV, the result will come out the same, right? And you don't have to worry about what the key is and all that. So it is possible that the attacker can change the IV and can change the plain text. And so you say money required and they will say no cash needed, that kind of stuff. So either must be fixed value as easy in electronic funds transfer at the point of sale, EFT POS. R must be sent encrypted in ECB mode before the rest of the message. So actually I have seen it sent in clear, so I don't know if people try to protect ECB. But main important thing is that you do not want to use IV again second time. Just like the key, every single time IV has to be changed. So if for the first message this is the IV, for the second message different IV, for the third message different IV. Because if you use the same IV, then you have given basically up more data to the attacker. So what they do is, so they use IV just once, and those things which are used just once are called nonce, N-O-N-C-E. Nonce means once, okay, no repetitions. The second problem with this is that you cannot really compute C2 until you got in C1, you cannot compute C3 until you got C2, so that's the problem. Sequential implementation, it cannot be parallelized. So before we go into parallel methods of parallel modes, there is one more thing we need to know is the padding. So what if the last block is not 16 bytes for AES or 64 bits for DES? Last block is partial of the message. Then we have to pad the last block. We have to add some extra bits to the last block to make it a full block. And so there are many methods of padding. It doesn't really matter which method you use, all of them cost you bits, because you want to send, let's say 65 bits, and you end up sending 64 plus 64, 128 bits. So these are some of the methods. One is that you just put zeros and then the count of the bytes added. So in this case, a 3-byte message and 5 bytes of padding. The last byte is the count. In another standard, they say one bit, just one bit, 1 followed by all 0 bits. In another one is, they say, well, you can just put 8-0, which is byte oriented. You just put 8, which is actually just a 1 in the beginning, 1 bit, and then all zeros. Some places they say just put random number. This is another standard which says just put random numbers. Another one says that you put the count every time, 0505, 0505. Another one says write the index numbers 1, 2, 3, 4, 5. Now, I don't think that one is stronger than the other, because it doesn't really matter. It doesn't really increase the security either way, because these are all standard. If you're using RFC 1570, everybody knows that this is 1, 2, 3, 4, 5. And if you're using this standard, then everybody knows that this is 050505. So plain text and everything is known for that part of the padding, right? So not one is not stronger, but basically it's a matter of difference. I put self-describing padding in kind of bold, because before I was aware of all these different standards, I was aware of this padding, which was mostly used. This is one of the most commonly used padding. This is called self-describing, because basically you know right away that this is the first padding byte, this is the second padding byte, and third and fourth and fifth. So make it easier. Another method alternative to padding is what they call Cipher Text Stealing, CTS. Is that what you do is you take the n minus first block, and the nth block is incomplete, right? So you take the n minus first block, you encrypt it, and the tail of it you give it to the last block, and then you encrypt it and you send it first, and you take the n minus first block and its remaining head you send later. So let's see what happens. The receiver gets this block here, and they know that we are using Cipher Text Stealing, so they get this block, they decrypt it, and they get the tail part of this, and they get the last block. Then they get this part, they add that to the tail to get this whole thing, then they decrypt it to get the n minus first block. So by this method you haven't increased a byte or a bit, right? And you have been able to get exactly the same number of bits transmitted as the original messages. And sometimes it is very important, for example on the disk, if you want to write 512 bytes, you want to write 512 bytes. You don't want to write 513 bytes. You are twice, any number. So anyway, so this is Cipher Text Stealing is an alternative to padding. All right. So basically, the idea is that the last one block, it's one part of it is sent earlier, and the other part is sent later, right? So you don't have to send this white space is not sent. Okay. Good. Thank you. All right. So now we are back to the track on other modes of operation, and these are called stream modes of operation, because in these modes, even though we are using block cipher, we are taking bit by bit and exclusive-ing them with something. So there are three modes that we will talk about. First is called Cipher Feedback, another called Output Feedback, and third one is called Counter Mode. And so in the Cipher Feedback, you take the initial value, you encrypt it with a key, then whatever comes out as a result, you exclusive are that with the plain text. Now you don't have to exclusive the whole thing, you could exclusive a part of it with the plain text, and then whatever comes out as cipher text, you feed it back there and you continue. So the first time you need the IV, other times you just use the cipher text. Now this is very similar to CBC, except that this part, before this exclusive R, does not depend upon the plain text at all. So you could calculate it beforehand, and when the plain text comes in, all you have to do is exclusive R and send it. No, actually this does not give that property. All it does is basically it does give you stream cipher in the sense that you get bit by bit streams and you don't have to have padding, but I think you cannot calculate the second block until you have calculated C1. Until you have calculated C1, you cannot calculate C2. Okay, so that property, what I said was wrong actually. So the correct thing is that, yeah, it does give you cipher text, but you cannot do it beforehand. Beforehand you can do it in this one, which is output feedback. In the output feedback, the feedback is taken right from here. Okay, now in this case, this dotted line can be implemented before you get the plain text. So this one actually again needs an IV, and the bit errors do not propagate. See, that's another thing, is that if suppose the C1 has an error in transmission, network error, then it doesn't affect C2 because all of this is pre-calculated the receiver, and as the bits come in, they're just exclusive or 1 bit error will cause 1 bit error. Somebody can modify the stream, and so they must remain in sync and only use with full block feedback. subsequent research has shown that only full block feedback should ever be used. So we had shown here this partial block feedback in this case, and here we have shown full block feedback, so that the whole result of encryption goes to the next level instead of some bits of that encryption. Okay, so that is OFB, output feedback. The fifth method is counter mode. In the counter mode, instead of having one IV, you really have a counter, and these counters are basically just count up. And so you initialize the counter in some particular method, and then they just count up, and then basically the result comes out which is different, because every time you send a P1, the counter will be different in different places. If you send the P1 again, the result will come out different. So this solves the problem of not replicating the same result, but a much simpler method. And you can do it in parallel, and you can do everything in advance, and it is good for high-speed links. Then it is also good for random access to blocks. So suppose you don't need C1, but you don't need P1 at the receiver, and you just need P2. For example, you have encrypted a disk, and you don't want to read the whole file, you just want to read the fifth block of the file. Then you just need to know the fifth counter, and then you can do the rest of it. And it is secure, and the main thing is that you don't want to reuse the same key and counter values. So the counters have to be initialized, randomly, and in some method, so that only the receiver knows how to do it. All right. So that brings us to the final discussion on storage encryption. So far we will talk about network encryption. We are talking about how to send the messages encrypted on the network. Well, there is an application here for storage as well. We want to encrypt a storage, and I don't know how many of you are using any encryption. I tried to use it, and it's always a pain, but anyway, so I gave up on it. But basically, you have two choices. You can do file encryption, or you can do disk encryption. File encryption, basically will encrypt whatever files you want confidential. The rest of the files will be visible. But even for the confidential file, other people can read the file name, creation date, size, and other things, because metadata about the file is not encrypted. And it is a standard feature in NTFS. So if you have Windows XP or Windows 7 or Vista, NTFS is there, and you can encrypt files, whichever files you want. So that is one way. Disk encryption. What if you want to encrypt the whole disk? Again, there are two choices there. You can encrypt partitions or encrypt the whole disk. All partitions. If you encrypt all the partitions, then you have two choices whether to encrypt the master boot record or not. MBR, because the way it works is to read the disk, first you read MBR. MBR tells you what the partitions are and where they begin, where they end. And so that could be in clear, right? If that is in clear, that is some information, and obviously if you are a defense department, you don't want anybody to be able to read even that. So then there are some methods of encrypting MBR also. But if you encrypt MBR, somebody has to know beforehand everything about that disk. So they need something called Trusted Platform Module, TPM. TPM is a secure chip, secure processor on the motherboard that keeps all this secret, and that can make sure that this disk can be read on this computer. If you take that disk and put it on some other computer, it cannot be read. It can authenticate the disk and authenticate the computer, each other. And so the question is, what if your computer breaks? What do you do with the disk? You lose the whole disk? Well, then there are ways out of that. So there is a decryption password, and the decryption password then somehow has to be supplied to some new computer, and then they are able to somehow recreate the disk. So decryption password, actually, as far as I am thinking, I was like, okay, I've never used this one. One is, you just, when you encrypt, you put that password. you create a password, and so you know the decryption password. As long as you remember that one, don't lose it. Yeah. All right. Let's see. Let me finish this slide anyway. So we cannot use CBC for sure, because we want to be able to so the thing is, first of all, CBC is not usable in storage because the plain text is chosen by the writer. So here's the thing: when you write on a disk, you are not the only one using the disk. There might be other people using the same disk, but they are not classified. Classified means they are not allowed to use the secret information, right? So because the computers are shared, the databases are shared, the storage is shared, there are people who are authorized to read the encryption information, and there are people who are not authorized to read the encryption information, but people can write some plain text, and so they can read their own thing, and they can figure out what system is being used. So there's another complication in the disk, which is not there in the network. Although networks are all shared, but you don't really share the final result, the receiver or anything. Here, the receiver is shared. So ciphertext is easily available to the other users of the same disk. Other people cannot read the plain disks, but they can always copy the whole disk. They can take it home after copying the whole file, and they can analyze it at home, right? Encrypted file. So need to be able to read, write blocks without reading and writing other blocks, and then we need the parallelism and independence, where every block should be able to be read without reading the whole thing from the beginning. And so CBC is not good. So what is good? So a new mode has been invented very recently, 2007, and this is called XTS-AES mode. We will continue this next time. So in this mode, which is basically used in the disk all over, they solve all these problems.